The first successful measurement of stellar parallax was made as recently as late 1830s, providing real information on the distances of stars. The thread of this talk will be to follow the major technological steps that have led from stellar parallax to the current generation of Allsky cameras and related devices and their many applications. Along with powerful computer analysis techniques, very affordable instruments are now available for a number of important astronomical and geophysical techniques. For example, the precise triangulation of the height and orbits of meteors and meteoroid trails, determination of the height and structure of the Noctilucent Clouds, the accurate tracking of scientific experiments using rocket-borne chemical releases, and the precise tracking of the reentry of major satellites, such as ATV-1, the ESA and NASA Jules Verne project, and practical examples of each of these will be provided by David. The talk will also cover the currently available image sensors that will provide very high sensitivity and low noise, fast readout speeds, enhancing the performance of these instruments. So we have a lot to learn about tonight, and for us it's going to be great help because we are now getting into the Allsky Cameras projects. We only did visual observations of meteors, and I'm kind of being thirsty for this speech. So let's enjoy our friend and let him share with us his knowledge. Welcome, David.
Thank you very much. Can I share screen?
Yes, of course.
You've just disabled my screen sharing.
Alexander, can you?
Yeah, yes, it's okay. Now.
Okay. Thank you very much.
It's still okay. You have to cancel your screen sharing.
Yes, Alexander, you have.
Right, that should do it, I hope.
Yes.
Can you see my screen?
Yes, Allsky Cameras. Yes.
Phew.
Yes, we do.
Okay, fine.
Okay, just wow, perfect. Let me take a picture of that before we proceed. Thank you.
I can send you the. I can send you this later on, so there's no problem. Right. Well, we've already had a presentation of what my abstract looked like, so I will just go through that very, very quickly. That, as I said, this really deals with Allsky cameras, some improvements that have been made recently, and basically there's an initial introduction to proper motions of stars of stellar parallax, because that's really where this whole business about triangulating against the stars, using stars as important references, where that came from. The background of the talk, again, was a talk that I heard from KITION a few months ago now, relating to their efforts to basically determine the positions and angles of incoming meteors. So I felt it should perhaps be done on a more mathematical basis. So I'm going to offer the possibility to discuss with young research workers the means that are used to actually do the triangulation of things like, well, rocket experiments or meteors, or the reentry of, for example, the ATV-1 spacecraft, Jules Verne, and go through that in some detail. So going into the business, starting off with attempts to measure parallax of stars, and the first efforts were really quite inaccurate, and the accuracy of the mathematical and instrumental methods were simply inadequate to allow this to be done successfully, until we were really into the well, 1800s, 61 Cygni turned out to be a fairly important star. It's only just about visible to the naked eye. Obviously, with telescopes at that time, it was more easily visible. But it had attracted attention of astronomers around the world at that time because it basically had a very large problem motion. In other words, its motion against background stars. At that time, nobody had any real idea of how far stars were from us. The distance scale of our own galaxy and the universe were really completely unknown, and it was something which was essentially the argument of the day. Where was the 8th sphere? In other words, beyond Saturn, nothing was really known. So that was the 7th sphere, and the 8th sphere was the fixed stars. Well, 61 Cygni turned out to have a significant proper motion. That indicated, of course, that it wasn't a fixed star, it was moving relative to other stars, and in fact, it ended up as being the target for Friedrich Bessel in 1838. He actually measured the distance by basically using parallax. And that really then started the whole process of precision astrometry and the ability to, first of all, work out where stars were, how far they were away from us, and then use it in the reverse sense of using these stars as to where they actually were at a given time, and use that as a basis for triangulation, which has really developed tremendously since the Second World War, really, and I'll explain why in a little while. Anyhow, it turned out that 61 Cygni wasn't the closest star, even though it was one of the fastest moving stars. It's not the fastest moving star. There are some fainter stars which actually move more rapidly. Nonetheless, is moving, well, if you looked at the numbers here, it's 4 arc seconds in right ascension, 3 arc seconds in declination per annum. The parallax, when that turns out to be measured, is 285 milliarc seconds. Very small angle, which explains, of course, why parallax wasn't measured accurately before this time. And this comes out then to be a distance of 11.4 light years, or 3.49 parsecs. Parsecs, of course, is the parallax as a result of the distance across the Earth's orbit. And essentially, 1 parsec is 1 arc second. And that, of course, means that something which is 1 parsec distance has a parallax of 1 arc second. The closest star, of course, is something like 4 light years, something just over 1 parsec away from us. So that is the first way that we have a real distance scale as far as the galaxy is concerned. Of course, at that time, things were very, very rudimentary. This, for example, is the actual parallax. Sorry, not the parallax. This is the proper motion of 61 Cygni, giving an indication of how much is moving against background stars over, well, really the decade from about 2011 to 2019. So the movement is quite significant, easy to determine. The 2 stars, 61 Cygni, is a nice double. And this is what its motion looks like over the best part of the decade. So it is a real effect, and that was why, of course, it was targeted as being the first star to actually be subject to parallax. What is parallax? Very simple diagram. Basically, the Earth's orbit about the Sun, and the nearby star is close, and we have the distant stars, and we're simply measuring the change of position of the star as the Earth moves 6 months through its orbit. Simplified diagram, but it gives a clear indication that, in fact, you can measure the parallax. And the argument really was quite fundamental in terms of what people were thinking in the 19th century, the early part of the 19th century. Even at that time, just over 200 years ago, the absence of parallax in stars was actually being argued as a reason why the heliocentric theory of the solar system wasn't correct. Again, back to the spheres, etc., with Saturn on the outermost sphere, and then outside that, the fixed sphere with all the stars, the eighth sphere. Basically, you could argue that we were way back into requiring all those cycles, epicycles, etc., in order to explain the apparent motion of the planets around the sun. Well, we now know that isn't required, of course. You just have the elliptical orbits around the sun. But, of course, the real issue was people just didn't believe, and this includes the top astronomers, didn't believe just how far the other stars, the next stars and nearest stars were actually from us. And that was the basic problem, that they had to essentially extend their whole concept of the shape and size of the, well, our galaxy in order to understand just how far these stars really were. So these gigantic distances were a real leap as far as our forebears were concerned. And that included people like Tycho Brahe, for example, who himself objected to Copernican heliocentric ideas. So we have gone a long way from that. Parallax now is measured on a very regular basis. Hubble made a lot of measurements personally, and now things like the very important stepping stones like the Hipparcos, the European Space Agency satellite, is primarily measuring both parallaxes and proper motion of the nearby stars, and this has increased the number of accurate measurements by tenfold the last, 20 years, 30 years, sorry, since Hipparcos was launched. Even so, even Hipparcos can only measure out to about a distance of 1,600 light years away from the Earth, which is only 1% of the diameter of the Milky Way. So while things have moved on, we still aren't there. An interesting extension of this is as a result of images carried out by the New Horizons spacecraft, as it, of course, has whistled past Pluto and then much further out into the distant parts of the solar system since then. And these, for example, are images of the same star field from the Earth and from New Horizons, basically blink micrometer, if you like, to show the motion, apparent motion of the nearby star against the distant stars. So this is working quite nicely, but of course, given everything that is involved with transmitting images from New Horizons, this is not going to revolutionize distance measurements throughout the galaxy, although the increased baseline from just the Earth's orbit diameter to the distance of New Horizons from the Earth is, of course, very, very important. And in principle, of course, it could give us a much bigger baseline for making measurements of much more distant stars than the 1,600 light years that we're limited to at the moment. So, ways forward in the future, nobody's actually proposed, as far as I know, a mission to go out there with a proper telescope to be able to make accurate parallax measurements from a much, much extended baseline. I'm sure it will happen in the future. Right, I'm going to switch now to the way in which triangulation is actually used within, if you like, things which are much more practical. This started off, by the way, not with the chemical Rees that I did my early work with using rocket launches from Woomera and other places, but in fact, Woomera and also locations in the USA were being used for studying the re-entry of missiles. And I won't go into great details as to what the missiles are supposed to do, leave that to your imagination, but missile re-entry was really quite an important thing. And as a result, networks of cameras were set up, really very accurate cameras in Woomera, around Woomera, and also in locations around the USA like White Sands, where various missile tests were being carried out. On the left, we have a Skylock Rocket, one of the ones that I was the principal investigator for in the early 1970s, or from the late 1960s into the mid 1970s, really. But this particular one was quite an interesting one, that it carried a number of instruments. We were measuring upper atmosphere winds during daytime, using quite a novel technique at the time, looking at the fluorescence in sunlight of lithium, which turns out to be very, very bright and therefore easy to track from the ground. Well, relatively easy to track. We had some interesting times with this. In fact, we were in a sort of competition with the Americans at the time, and with the whole resources of the US Air Force, we beat them to it. Friendly collaboration as well, but we actually made the first successful measurements about a year ahead of the Americans, so we were quite happy with that. Other instruments on board this were measuring the ionospheric electric field, magnetic field structures, and looking at the magnetic field fluctuations as a result of the daytime electrical currents that occur in the ionosphere. So we were measuring the winds connected with those, we were measuring the electric fields connected with those, and the actual magnetic perturbations as a result of the electric currents that were flowing. Well, as you probably remember, we only ever launched one satellite with the Black Arrow launcher, and nonetheless, using the high-altitude rocket experiments, we had a very successful program, did a lot of good science, and arguably we led the way globally for many techniques of measuring the upper atmosphere, and also for ultraviolet and infrared space astronomy. Using the techniques that we developed, a number of research groups within the UK, primarily Birmingham, Mars Space Isotope Laboratory, UCL, also Imperial College, and Leicester, for example, who were very successful at winning access to flight opportunities within NASA programs and also the European Space Agency's program. So we can count our early experiments with these high altitude rockets as being very, very successful at sort of cutting our own teeth in terms of instrumentation development, and also giving us the confidence that we could make good proposals for future flights within American and European space programs. So what were we doing with triangulation? Well, that particular rocket experiment was racing a lithium trail in daytime, and we had to triangulate that trail without stars. We had to use other methods for getting an exact, essentially, picture of where the instruments were looking. So we had to basically operate the systems during the rocket flights at daytime, and then operate the same equipment in daytime, at nighttime following the experiments, and then calibrate the instrument fields of view using the nighttime observations. That was difficult, but it worked. The rocket flight on the left here is basically a rocket flight from Kiruna, northern Sweden. And one of the experiments we were using at that time was the grenade experiment. So you see all of these flashes that are going up along the rocket trajectory. Those flashes basically are from grenade explosions. They are photo flash grenades, but quite powerful flashes. And then in order to be able to make the scientific measurements, which were basically detecting the arrival of the sound waves, shock waves from these grenade blasts on a network on the ground over quite a few square kilometers using ultra-sensitive microphones. And basically, in order to make the experiment work, we had to determine with flash detectors the actual explosion time with millisecond precision. We had to triangulate the flashes themselves with a precision of 1 or 2 meters in order to be able to get the distortion of the sound waves with enough accuracy over this network of ground-based microphones. We also then used this network of ground-based, film-based cameras in order to do the triangulation. Of course, all of this was 20 years before CCDs, etc., were in anything like widespread use. The camera images then had to be synchronized within about 1 second. Looking at the upper part of the trail, you'll notice this sort of spiral structure, which is actually the winds in the upper atmosphere from about 85 kilometers up to about 120 kilometers, basically distorting the trail, trimethyl aluminum trail, and that basically is used to measure winds, again, by triangulation against the stars. You can see some of the stars in the background, particularly ones on the right-hand side. So that was basically what we were looking at. The nice thing then, which became very pretty, which had a downside, which I'll get to later on, the trimethyl aluminum trails glow by means of a photochemical reaction with atomic oxygen at low altitudes and at nighttime. When they get into sunlight, and this particular experiment, in fact, went into sort of pre-sunlight, and then the sun rose on the TMA trail, and that makes a beautiful turquoise blue color. And from that, we can measure atmospheric temperatures and density from the diffusion of the clouds. So we get a wealth of information, wind velocities, temperatures, densities of the upper atmosphere from observing these trails and the clouds that come from these grenade explosions. Grenade explosions themselves are aluminium based, so there's a lot of aluminium around, and so this aluminium oxide, which is produced, as I said, it generates this fluorescence emission when there's sunlight. So this, for example, now is the Aurora Skylock Rocket, nighttime flight this time. The trail going upwards from the bottom, starting about 85 kilometers, and then going all the way up to about 240 kilometers. The upper part of it's in twilight, so it's got this beautiful turquoise color, and you see the complex wind structure that is resulting from the atmospheric winds twisting the trail around in different directions, different heights. So from the triangulation against the stars, we measure those wind velocities. Again, density and temperature coming from the aluminium spectra and from the diffusion of the clouds. Again, we're using triangulation for this. In the upper part of this, these photographs, both on the right and the left, you can see some sort of purplish clouds, reddish purplish clouds, and they are barium clouds. And you can see on the right-hand side in particular, elongated region, which is the barium ion cloud, produced by ionization of the barium neutrals, and then also a greenish cloud on the lower part of those elongated clouds, and that's due to strontium and neutral barium. So we get a lot of data on atmospheric densities and temperatures, as well as from the ion clouds, the measurement of the ionospheric electric field. So a wealth of data that comes from these. Of course, it's fairly expensive, launching rockets, etc. And as a result, you can't really get into the climatology of the atmosphere from this means. If you look on the left-hand side, you will recognize Orion from its belt, 3 stars. But you also notice it upside down, of course, Australia again. One of those problems, but matching the star field, of course, is one of those things that's very important if you're trying to do this triangulation. So again, same sort of techniques, now launches from Kiruna, northern Sweden, where again now we have a barium cloud, and you see the striations in the barium cloud, and then also the neutral barium cloud. The trail in this case is sodium rather than aluminium oxide, or trimetal aluminium. And the first one is quite early on. The second one on the right-hand side is something of the order of 30 minutes later. And from that, you see that the barium cloud has become quite striated. And the striations in the barium cloud are in fact quite similar in structure to what we often see with the striations in auroral forms. Of course, they're both responding to the ionospheric electric field, and therefore it's not surprising that they show similar structures. This next one is an interesting one we did from Alaska. So this was basically a flight with support from the people at the Geophysical Institute, University of Alaska in Fairbanks. The first stage of the rocket, you see the entire parabolic flight from ground up to apogee and then down again. Put hard hats on if you're anywhere near the landing zone. Second stage then goes upwards from that, and a very short part is the third stage. So this is a 3-stage rocket taking the barium-shaped charge releases to a height of above 1,000 kilometers. The shaped charges detonate and release the barium neutral at that time with a velocity of something in excess of 10 kilometers per second. That means it's basically got the escape velocity, also got enough velocity that in fact the ions, the neutrals will ionize themselves very, very quickly by a combination of collision and charge exchange with the ionospheric ions. So you're not only depending on the sunlight to create the ionization. Using these techniques, we're actually able to create fast-moving jets which can be tracked all the way out to the equator and beyond. So we can explore the Earth's ionosphere and magnetosphere out to distances of the order of 40,000 kilometers using these techniques. These particular ones were being used as a sort of experiment in advance of some releases which were put on the empty and later the CRES satellites. These two NASA satellites with UK participation and a lot of international participation, and they were used to create sort of artificial comet experiments, including ones which went out into the solar wind, and therefore we could emulate exactly what was happening in terms of the interaction between comets and the incoming solar wind. And in particular, they showed some of the early ones of the empty releases showed that in fact the creation of pickup ions, where the solar wind basically flows into the cold plasma produced by the releases and then ionizes, excites, heats, and then accelerates the barium ions, and basically pushing them up to a very high velocity as well as a high temperature. And we had the data on that from the first of the empty releases, which was again a global first. So I'm going to do a switch now. For many years, there'd been sort of UFO-style reports from airline pilots and others of funny things that were going on over thunderstorms. And as in the case of UFOs, of course, yes, there are the believers and there are the non-believers. Unidentified, yes. Evidence of extraterrestrials, no. But it turned out that, in fact, sprites and related phenomena were very real. The thunderstorm, of course, itself, particularly intense ones, are very bright. The flashes are very bright. The entire cloud above the thunderstorm, if you observe this at night, is brilliantly lit. And of course, that means that it's extremely hard to observe anything directly on top of an active thunderstorm. And yet, these are the sprites. In the atmosphere, lower parts of the ionosphere, extending up to sometimes over 100 kilometers. Quite brilliant, but you can't see them from nearby. Again, because of the brilliance of the lightning flashes themselves. They occur very shortly after it when, if you're observing by eye, you would either be blinded by other lightning flashes from nearby clouds or active clouds, or alternatively, your night vision would still be severely compromised, so you wouldn't be able to observe very much. So how do we observe sprites? Well, the answer is you go some distance away, go to a high mountain, hide yourself in a high mountain, use the curvature of the Earth, and your sprites are sort of over here, and now the cloud producing the thunderstorm, the thunder is below the horizon, out of sight, and therefore not blinding the observers, not blinding the cameras, etc. So that allows us then to have a clear observation run of the sprites themselves. So that basically has been the way in which some of my colleagues from the University of Alaska, again, have been working extremely hard to make these measurements over the last sort of 20 years or so. As I said, it really has proven there's a real phenomena, a very complex phenomena, blue streaks and other phenomena that occur in association with these. It's a whole sort of zoo of phenomena that occur on top of major thunderstorms. So very successful observations from, well, again, people from the University of Alaska and other groups from the USA have been working hard on this. And of course, CYPRUS could be a very good location to go looking for these things. You have high mountains and you have these distances, and therefore there's some chance of making these observations in addition to meteors. So if it's too cloudy for meteors, then go looking for sprites.
David, actually, this was my question, because I'm a thunder chaser, so I'm trying to take thunders on camera. And yeah. I was going to ask you, what is the ideal altitude that you have to avoid the curvature of the Earth, because the highest point here is 1,951, which is Troodos. It's very far away, very far away. What is the minimum altitude?
Oh, 1,000 meters.
1,000 meters.
Yeah, I mean, you're primarily using the curvature of the Earth to do the hiding of the active thunderstorm itself. Okay?
Okay, so about 1,000 meters.
Anything above 1,000 meters is going to be good.
Thank you very much.
So now
I will dedicate my first photo to you.
Okay, good. Coming back now to more details of how triangulation is done. This work is some work that I did with Hans Nielsen of the University of Alaska, Fairbanks, back over 10 years ago now. We were doing triangulation of the reentry of ATV1, which is planned in advance, so it is all well known exactly when the project was going to occur, what time it was going to occur, the expected orbit of the ATV as it re-entered the atmosphere. So the basis really is we have stars, a star chart as you see here, and then basically we have to identify what the stars are. So there are programs that do that. So you see we've now progressed to having the identification of the stars down to quite faint stars as well as quite bright ones, and that is the basis on which the triangulation can occur. That gives us exact information on the position of the stars in terms of obviously their right ascension and declination. We can then translate that into positions in on relative to a ground-based system, altitude and azimuth. From two stations then, if we have a suitable distance between the two stations, we can then use that information to triangulate using two, possibly more stations in order to get the exact positions of the objects that we're trying to track. In the case of this project, we were trying to track as many objects as possible during the breakup of the ATV-1 spacecraft as it re-entered the Earth's atmosphere. And as you'll see, that became quite a challenge. Anyhow, we go from that, where we're identifying the stars, and now we basically look at of the re-entering ATV-1, a time when in fact things got very active, where a major oxygen tank on board the ATV-1 had just got to its critical point and exploded. That's this brilliant glow cloud. The other apparent objects here are not real objects. They are actually just due to the reflections from the windows of the aircraft, which unfortunately one has to have there to be able to fly at 35,000 feet. So one of those things one has to tolerate. So in this case, we've got the star, well, we've got the image file, this top one, the bitmap file, and then we've got the star file below that. The two have been merged so that we can see where the stars are and use those for the triangulation or to give us the exact elevation as a function across the field. So again, now we're looking at another point of re-entry, and the major interest that ESA and NASA had was related to objects around this area here. Right at the front of this, we would expect after that major explosion, which to a large extent turned the ATV into fragments rather than a complete spacecraft, there's one very heavy object, the attachment ring between the final stage of the Ariane 5 rocket that launched the ATV and then the ATV itself. That weighs 2 tons, and people were very worried about where they would land. Basically, that they could accurately calculate where it would land, so that if they started the re-entry procedure at the right time, they would know exactly where that would land, and therefore obviously make sure that there were no aircraft, ships or anything else around that area, and obviously that it re-entered well away from any inhabited areas. So that was our challenge, really, to work out where this particular object, and as many other objects as we could track, would actually land. So step by step, we have the image and that is the image here from one of the sites. And then we bring in the image from the second site at the same time. Now they look very different because the aspect of the two aircraft that were tracking this were very different. One was the DC-8, and the other one was a Gulfstream. So we've brought in now the two sites, this being the one, and then this being the second site, and now we can pick up objects that we can identify clearly, or we think we can identify clearly from both of the images, and then we can run through and do the triangulation. And all the mathematics for doing that is embedded within this software. So this is a stereo system that actually takes us from working from individual stars and the identification of the objects, going through into the stereo version, which allows us to do the full triangulation by simply identifying points from the two sites, and it gives a sort of least squares fit. If you do the triangulation, you basically get some sort of crossover where they don't cross over exactly, and then you can minimize that to ensure that you are actually identifying the same feature from both images. So that was a lot of fun, a lot of hard work, but it did work out rather nicely, and then we were able to go through that. This then shows exactly what happened, where we were able to measure the reentry path of the ATV. This is longitude versus latitude, and then you see the altitude here, and you see sort of typical errors occurring during the mathematical analysis. Both aircraft had to maneuver quite violently in order to be able to get the best tracking of the re-entry path. Again, the two paths were quite, or seen from the two aircraft, the paths were quite different. Obviously, we were trying to make sure we could observe both, observe all the features, all the key features of the re-entry from both aircraft over as long a period as possible. We did a pretty good job on that. I'll come back to that in a short while. So the target again was pick up the heaviest component, which was that attachment ring, make sure we knew where that was going to go and where it landed, make sure that landed more or less where they expected it to land. You then have a sort of, a dispersion pattern of where the other items land, and I'll show you exactly what is involved with that as we go through some of the images. So it's not only used for the business of the ATV, we use it for rocket experiments. So these, for example, are some illustrations of a system that's also used at the University of Alaska by some other colleagues of mine, Mark Cohn, and this was looking at ion releases, rocket-borne ion releases from Andøya, northern Norway, 69 degrees north, and looking at the actual images, which are these blue clouds here, and then tracking these, and obviously going through the triangulation, nominal altitudes, so that we could actually work out where we were. The horizon, as one would see it from different stations. A more complex situation now, where again we're looking at a black and white image in this case. But we've got the star background identified in this, and we've got the actual chemical releases, and then we're trying to work out the motions of these releases, the height, and then the velocities, wind velocities, ion velocities as appropriate. And this one is then again a combination of the two, and there are some, well, I think these are put in by hand, sprites and related things at lower altitudes. The sprites are mainly sort of below 100 kilometers, 110 kilometers, whereas these releases go up to about 400 kilometers, and even above. So, other applications. Well, this is one of the Allsky camera images that I've been working on. It's using basically a very nice QHY 600 camera. Does a very nice job on the Milky Way. Also does a very nice job on clouds, of course, tropospheric clouds. But nonetheless, this part of the sky is very clear, and well, Milky Way comes out rather nicely considering it's just in monochrome. So with this camera, we were successfully able to image a few of the Perseid meteors from a few weeks ago. And this is a rather long meteor trail. Funnily enough, brightening up sort of twice at high altitude, dimming, and then brightening up again, and then exploding into a fireball, probably around about 40 kilometers altitude. So it's an unusually long trail. This other trail down here is in fact a satellite, one of the many, not one of the Starlink ones, but one of the many. But again, we have the Milky Way in the background, so another nice image. Another Perseid coming in, the trail here again brightening up very quickly and disappearing, so we don't have, well, it's quite a different sort of trail compared to the previous one. Looking at that close up, you can see that basically it brightens up considerably, but then continues quite a long time, again behind the clouds a little bit, but not stopping everything from being seen. So I'm going to go through the reentry again. Again, all the features we're trying to get. This was the key one here. The way that we get the data on what object is what is we actually get the spectra. In addition to the images, we have the spectra. So we can identify the metals that were in fact being heated, obviously to many thousands of degrees, and therefore able to give off the atomic lines as a result of the excitation process as the ATV re-entered the atmosphere and broke up. So this is what the breakup looks like later on, many features. And all of this is accurate timing. So these now are a sequence of the images. You see the trail forming here as the objects start breaking off all the little bits and pieces. And then we get this sort of explosion as it gets lower down, it gets superheated and then blows up. So again, I'm going to talk now about a little bit about the Allsky cameras themselves, some special arrangements that I've been using with the Allsky cameras. The QHY 600 is one of several devices we've been loaned by QHY. QHY 600 is the one I'm going to show some images from here. We've got a 4040, which is a very nice camera, 4,000 pixels by 4,000 pixels. This one is 6,000 pixels by 5,000 pixels. So it's a very large chip, lots of pixels, 120 megabytes of image. You take the full 16-bit image. The target has been to identify which of these cameras might be most suitable as a CMOS camera for use within the Exoclock project, currently looking at the updating the ephemerides of exoplanets for the Aurora satellite project. I showed you some of the images earlier on from Milky Way and meteor impacts, and then basically we'll go through and look at some other ones that we're running. This is a simple image of the combination of a Canon Allsky lens, 180-degree lens, ahead of the QHY 600. And then on the right-hand side is a simpler, cheaper option. Basically, it's another wide-angle lens mounted just ahead of an ASI, the ASI 224. So we can use the two of these in comparison. No question about it. One on the left with far more pixels, of course, produces by far the best images in terms of resolution and coverage. But nonetheless, they're two options. The cheap one on the right, the much more expensive one on the left. They really produce, on the other hand, both of them, rather nice images of the sky. Again, this one with the meteor trail here was produced by the QHY 600 camera behind that Allsky lens. And
may I interrupt you? When you say you go to your previous slide, can you go to your previous slide, please?
Yeah.
So it's not a factory made. It's a customized one, not like the ones that we find online to buy. And I see it's using the camera with an add-on of a Canon lens on the left, and the other one to the right is similar. And
yes, with both of these, the cameras are bought in QHY on the left-hand side and the ASI camera from ZWO on the right-hand side, and then one has to adapt to be able to mount the Canon lens up front. Non-trivial, a little bit of engineering, but that is custom. But they're both custom adaptations of the lens to the camera. They don't come supplied like that. You have to put them together yourself.
And when you say low cost, what do you mean by low cost?
Well, the ASI 224 is somewhere around £200, between 160 £200, and the lens is probably about £100. So this combination here is something like £300, the whole thing, lens and the camera. On the left-hand side, on the other hand, this is a sort of £200 lens, maybe more than that these days, and the camera itself is about £4,000 to £5,000.
Yes. Okay.
So it's affordable, top end astronomy. I've been using the the QHY 4040 on my 16-inch telescope with some quite nice results.
So we can adapt the MC533, the ZWO, MC533. We can adjust it. We can connect it directly to the lens, and it's finished.
Yes, that's right. I mean, you just have to get the right back focal distance, so the image from the lens is in focus and aligned to the detector sensitive plane. It needs to be done carefully and stably, obviously, so it doesn't rattle around, but it can be done. So these are some images. And again, I'm very impressed with the QHY cameras. If you look at the background of this image, you see the clouds here. Okay, I can't do much about that on this particular night. They were just there. But it's a very uniform background and a very low background. The camera was running -10 centigrade with an inbuilt anti-cooling system. If I compare that with this image now with this is with the ASI 183 from ZWO on my 16-inch telescope. Horsehead Nebula.
Wow.
Nice bit of astronomy. Yes. So, sorry, come back. Right. But you see this line going across here. Now that's the glow from the CMOS camera. The ASI 183 suffers this glow, and you see it actually spreading out sort of from a point on the left here. That's one of the annoying things about the ASI 183. Yes, you can correct that, you can calibrate that and take it out of the images, but the raw images all have this sort of glow over them. And if you try to produce really nice images, so I'm very much in favor at the moment of the QHY cameras. Yes, they're a bit more expensive than the ASI cameras, but the quality of the images, in my view, is very, very good. This camera was running about -25 centigrade at the time, so it wasn't thermionic emission or thermal leakage from the CMOS device. It was this glow from the device. As I said, the QHY cameras just don't have that. So what else do we do with these? All sky, right, fisheye lens, and a field lens, and then another field lens. And what we can do is then go into high resolution spectroscopy using 1 or 2 Fabry-Perot etalons in this space here, and then of course we image onto our detector. So trying to make a fast system, because we're looking at, in this case, rather faint objects. In fact, it's a bright scene. We're running a daytime experiment, and we're looking at the airglow auroral emission of 6300, the oxygen red line, and we're trying to observe that during daytime, which is a bit of a challenge. But it's something we've done. Instrument, okay, it gets a bit complicated because one has to mount up the 2 etalons, as in here, and obviously the all-sky lens, and then the rest of the system. So it's a bit of a beast when it comes together. This image on the right-hand side gives some idea of what it's like. It's sort of 40 centimeters diameter and about 60 centimeters long, all sealed inside a tube, which is then pressurized. Just at 1 atmosphere, but kept constant pressure at one atmosphere, and it's thermally controlled. What are we doing with all of that? Right, the system is looking at the zenith, and it is observing more or less the whole sky. And this is what it sees. It produces a spectrum in real time. The oxygen emission from Aurora is actually this bright line here, a bright circle here, going all the way around. So this was a first, again, a global first. We can measure the spectral lines very carefully. Of course, the Fabry-Perot has a parabolic relationship between distance from the center and the wavelength. So we have to make allowance for that. And that is basically what's done here. And you see then again, the oxygen emission isn't actually earmarked because it's the absorption lines in the solar spectrum, Fraunhofer lines, that are actually identified in the spectrum. But that weak emission line going all the way around is actually the oxygen emission, bright ring. So there's a bit of filtering involved to get that. This was done 20 years ago, by the way. It wasn't exactly last week. For one reason or another, we've never managed to quite get back to running this on a regular basis. We did some careful work. Mark Conde and I were doing this, I said 20 years ago, 22 years ago to be exact. So again, the oxygen emission, you see this blue feature here, corresponding to this bright ring. This is done by basically then putting these rings together, and then we get the first ever image of the aurora during daytime, as shown here. Bright features and dimmer features. This is basically by putting 10 consecutive images as smoothing these as the Fabry-Perot atoms are scanned through one complete free spectral range. So that's the way this image has been built up. It's not an instantaneous image. It takes of the order of about 5 minutes, actually. The primary problem at this time with the CCDs that were in use in 1999, it took a long time to download the images. And that download, basically each of the images took something of the order of 30 seconds to download. So that limited the time resolution that we'd get for the overall imaging. Not the easiest thing in the world to do. Well, we managed to get observations on quite a number of days in a couple of periods we did, both in year 1999 and then again a rather better sequence in 2000. And then we look at this, you see the image now over about an hour-and-a-half period. So that was indicating that we got consistent patterns in the aurora over that sort of hour-and-a-half to 2 hours period. So we were pretty happy about that at the time. And so it's been one of my regrets that we never actually got around to doing this. So, reentry. Back to this as a more or less lead on this. Right, so I thought that would be a good way to show it. ESA spent nearly $1 million, or sorry, €1 million on the camera that took those photographs. We couldn't use a single bloody image from that whole sequence because there are no stars. Of course, with the aircraft moving around and the camera obviously being handheld rather shakily, as I said, we couldn't use a single image from that entire beautiful sequence, but I thought it'd be useful to just give you an idea of what one of those re-entries actually looks like. They are spectacular events, as one of the gentlemen on board the aircraft said in real time. You have to feel sorry for the guy, Michael, who was told to keep looking because he was foresighting a spectrometer that was supposed to be duplicating the spectral images taken from another instrument which was working to help to identify just what of the metallic objects were actually burning up in the atmosphere and creating the different atomic spectra that we use to identify just which bits and pieces of were which. But we managed to identify the titanium disk, the 2-ton titanium disk, and many of the other components that ESA and NASA were extremely interested to be sure that they all fell within what was the predicted path of the objects breaking off the ATV-1. So, job done. So, thank you very much.
Thank you, David. Thank you very much. A great presentation, very interesting. Some things that first time I came across. Incredible presentation, incredible images. I'm really impressed, David. It was really informative. Thank you for sharing with us. Any one of our colleagues who would like to ask any question? To David?
Captain Spock, you do not stand accused. Mr. President,
Sorry?
I stand with my shipmates. As you wish. The charges and specifications are conspiracy, assault on Federation officers, theft of Federation property.
Are we watching a TV? Are we watching TV? Are we watching? We are listening to you. Okay. Anyone would like to ask any questions?
David, has much of your work been replicated by the Gaia project?
You're talking about now the preparations for the exclot work is going on at the moment. Is in,
yes.
Basically is going for the Ariel project, which will be launched in 2028, and Ariel will go way beyond what other missions have done because it will be basically looking for the spectra of the atmospheres in addition to just the fact that the exoplanet transits are occurring.
Yes.
With each one of them, it will be looking for the different spectra from the atmosphere, the absorption and emission spectra from the atmospheres of the exoplanets. So that's something that hasn't really been done in any great detail.
Yeah.
The Twinkle mission, which should be launched in 2 years' time, 2034, that will start some of this work on spectra, but the instruments on board the aerial satellite are just that much powerful, and obviously with 3 or 4 more years to actually prepare the instruments and get ready for the launch.
Yeah.
So the answer is it's building, as usual with these things, building on the experience that's obtained. Obviously, Gaia will have, and TESS also producing some very interesting results at the moment. And it really is just building on what they're learning in terms of the motion of the individual exoplanets, yes, their orbits, etc., mass distributions, all that sort of thing is essentially up for grabs at the moment.
Right, thank you.
Great. Any other question?
Obviously, too much history.
I have a question, David.
Yeah.
When are you coming over to set up our camera?
Well,
John,
I think
John Fox is laughing, you know, because he has been setting up everything that Hesman should tonight, so that's why he was a bit late. I apologize.
I am due to be in Athens in July next year, so maybe a trip from Athens to Cyprus.
Yes, why not?
I've been hoping that the international travel regulations re COVID-19 are a lot easier by that time. But you know, 11 months time, things should be a little bit easier. Cross fingers.
I hope by that time we will not have COVID 21 plus. The new version.
which variant's going to hit us next? Yeah, that's the big worry. Yes.
Okay, so okay. Anyone else? Questions?
Looks like I've frightened people with too much maths.
No, that was not too much math. It was for me. It was really, really interesting, and I have captured some photos with that I will come up with some questions later on.
Yeah, okay, I'll be around. You know where I am.
Yeah, of course I do. Yeah. So, Alexander?
Yes, so let's then make some more announcement. At the beginning, I already said that our read is expected to give max outburst today. So the moon spoils everything, but anyway, if we use whole sky cameras, then we shouldn't observe by ourselves, and some bright meteors could be at the could be caught. Well, another point what is going these days is Mira, the Omicron Ceti star. It is at maximum already, and it was observed. This is its observation, the dates and the magnitude. So it was very bright, up to 2.2 magnitude, and it was just at the beginning of months. Now it is end of months, and it's closer to 3 magnitude, but it's still really bright. So where we have to look, if we are taking again to the same field of view, so here is our read is, here is the moon, then we have to look at this point. It's Omicron Ceti, which connects the front and the rear part of the constellation. So usually there is nothing here at all, but today we will see something bright. And I recommend to observe it with telescopes as well, even with binoculars, because of binacti +3 is just a white dot. But with telescopes, you will clearly see that it is red color. And this is our next event. So on the 28th of September, we will have online science cafe dedicated to World Space Week all over the world. We will celebrate it starting from the 4th of October formally, and in fact, around those days, the way which is available.